Have you ever wondered about where the Earth is located in the universe? It's a fascinating question. Let's imagine the universe as a gigantic, vast space that is filled with so many things like stars, galaxies, and other amazing objects. A long time ago, people thought that the Earth was at the center of everything. They believed that the universe was made up of the planets they could see with their eyes, like Mercury, Venus, Mars, Jupiter, and Saturn. They also believed there was a big sphere made of bright stars surrounding these planets. But then, some really smart people, like a scientist named William Herschel, used a special tool called a telescope to look deeper into space. They discovered that the Sun, the star that gives us light and warmth, was not at the center. Instead, they found out that it was part of a huge group of stars called the Milky Way galaxy. It's like a big, flat disc-shaped collection of billions of stars, and our Sun is just one of them. If we go a little further, we come across the outer space. Outer space, often referred to simply as space, is the vast expanse that extends beyond Earth and its atmosphere, stretching between celestial bodies. While it may seem empty, outer space is not completely devoid of matter. It is a near-perfect vacuum, characterized by a low density of particles. The predominant constituents are hydrogen and helium plasma, accompanied by electromagnetic radiation, magnetic fields, neutrinos, cosmic rays, and dust. The background radiation from the Big Bang sets the baseline temperature of outer space at a chilly 2.7 kelvins, -270 degrees Celsius, -455 degrees Fahrenheit. Within the vastness of space, the plasma residing between galaxies is estimated to account for roughly half of the baryonic matter present in the universe. However, its number density remains extremely low, with less than 1 hydrogen atom per cubic meter. This intergalactic plasma exists at temperatures reaching millions of kelvins. Despite the low density, localized concentrations of matter have condensed over time, giving rise to the formation of stars and galaxies. Even within galaxies and star systems, empty space dominates the overall volume. Furthermore, the majority of the remaining mass energy in the observable universe is composed of enigmatic entities known as dark matter and dark energy. If we go a little further, we come across Earth's orbit. Earth orbits the Sun, maintaining an average distance of approximately 149.60 million kilometers, 92.96 million miles, in a counterclockwise direction when viewed from above the northern hemisphere. It completes one full orbit, known as a sidereal year, in about 365.256 days, covering a staggering distance of approximately 940 million kilometers, 584 million miles, during that time. While disregarding the influence of other celestial bodies within the solar system, Earth's orbit can be described as an ellipse, with the Earth-Sun barycenter serving as one focal point. Currently, the orbit's eccentricity is measured at 0.0167, indicating a relatively small deviation from a perfect circle. As a result, the center of Earth's orbit remains fairly close to the center of the Sun, relative to the overall size of the orbit. Observing from Earth, the planet's orbital motion in the prograde direction makes it appear as though the Sun is moving approximately 1 degree eastward relative to other stars each solar day. This is equivalent to the apparent motion of the Sun or Moon by the diameter of the Sun every 12 hours. Earth's average orbital speed is about 29.78 km per second, 107,208 km per hour, 66,616 miles per hour, enabling it to traverse its own diameter in a mere 7 minutes and reach the distance to the Moon within approximately 4 hours. If we go a little further, we come across the inner solar system. The inner solar system is a fascinating region that includes the terrestrial planets, such as Earth, Mars, Venus, and Mercury, and the asteroid belt. It is characterized by its proximity to the Sun and its composition primarily consisting of silicates and metals. This region spans a radius smaller than the distance between the orbits of Jupiter and Saturn, highlighting its relatively compact size. It is worth noting that the inner solar system is also situated within the frost line, which is approximately less than 5 astronomical units (AU) from the Sun. To put it into perspective, 1 astronomical unit is equivalent to about 150 million kilometers or 93 million miles, so the frost line is around 750 million kilometers or 460 million miles away from the Sun. The inner solar system is a region closer to the Sun, encompassing the terrestrial planets, including Earth, and the asteroid belt. Its composition is mainly composed of silicates and metals, and its overall size is smaller than the gap between the orbits of Jupiter and Saturn. Furthermore, it lies within the frost line, which is located at a distance of a little less than 5 astronomical units from the Sun, equivalent to approximately 750 million kilometers or 460 million miles. Moving little further, we are in the outer solar system. In the outer region of the solar system, we encounter the majestic giant planets and their expansive moons. This region also accommodates the centaurs and numerous short-period comets, which orbit within its boundaries. The solid objects found in the outer solar system, such as asteroids and comets, exhibit a distinct composition compared to those in the inner solar system. The greater distance from the Sun in this region allows for lower temperatures, facilitating the presence of higher proportions of volatiles like water, ammonia, and methane. These compounds can remain in their solid state due to the colder conditions prevailing in the outer solar system. The outer region of the solar system hosts the giant planets, their substantial moons, the centaurs, and short-period comets. The objects in this region possess a higher concentration of volatiles, including water, ammonia, and methane, compared to those closer to the Sun. This disparity arises from the lower temperatures prevailing in the outer solar system, which allow these compounds to remain solid. Next comes the Kuiper belt. The Kuiper belt is a disc-shaped region located in the outer reaches of the solar system, extending from the orbit of Neptune at approximately 30 astronomical units (AU) to around 50 astronomical units from the Sun. It is analogous to the asteroid belt but is significantly larger, being about 20 times wider and 20 to 200 times more massive. Similar to the asteroid belt, the Kuiper belt primarily consists of small celestial bodies that are remnants from the early formation of the solar system. However, unlike asteroids that are predominantly composed of rock and metal, the Kuiper belt objects are composed mainly of frozen volatiles, such as methane, ammonia, and water. The Kuiper belt is notable for being the home of several dwarf planets recognized by astronomers, including Orcus, Pluto, Haumea, Quaoar. Additionally, some of the moons in the solar system, such as Triton, Neptune's moon, and Phoebe, Saturn's moon, are believed to have originated within the Kuiper belt. It is important to distinguish the Kuiper belt from the hypothetical Oort cloud, which is presumed to be located at a much greater distance from the Sun and has a more spherical shape. Collectively, the objects within the Kuiper belt, along with the scattered disk and potential members of the Hills cloud or Oort cloud, are collectively referred to as trans-Neptunian objects, TNOs. Pluto, previously considered the 9th planet, is the largest and most massive known object in the Kuiper belt. Its classification as part of the Kuiper belt led to its reclassification as a dwarf planet in 2006. Pluto shares compositional similarities with many other Kuiper belt objects, and its orbital characteristics align with a subgroup of TNOs called Plutinos, which share a 2 to 3 resonance with Neptune. The Kuiper belt is an expansive region beyond Neptune that consists of small icy bodies primarily composed of frozen volatiles. It is home to several dwarf planets and is distinct from the Oort cloud. Pluto, the largest member of the Kuiper belt, was reclassified as a dwarf planet in 2006. Moving vast distances, we reach the heliosphere. The heliosphere is a gigantic bubble extending into space, encompassing the Sun, and reaching far beyond the outermost planets like Pluto. It is created by the continuous outflow of charged particles, called the solar wind, originating from the Sun. This stream of plasma expands and forms a cavity in the surrounding interstellar medium, giving shape to the heliosphere. The heliosphere serves as a protective shield for our solar system. As part of the interplanetary magnetic field, it helps deflect and redirect significant amounts of cosmic ionizing radiation, safeguarding us from its harmful effects. However, Uncharged gamma rays can still penetrate through the heliosphere unaffected. The term heliosphere was likely coined by Alexander J. Dessler, who introduced it in scientific literature back in 1967. The study of the heliosphere and its properties falls under the field of heliophysics, encompassing aspects like space weather and space climate. As the solar wind travels through the solar system, it flows unimpeded for billions of kilometers until it encounters a region called the termination shock. At this point, its motion abruptly slows down due to the pressure exerted by the interstellar medium, which fills the space between stars. Beyond the termination shock lies the Helios heath, a broad transitional region between the termination shock and the outermost edge of the heliosphere known as the heliopause. The heliosphere's overall shape resembles that of a comet. Voyager 1, for instance, reached the heliopause on August 25, 2012, where it detected a significant increase in plasma density. Voyager 2 followed suit and crossed the heliopause on November 5, 2018. After trillions of miles, here comes the Solar System. Imagine a vast, gravitationally bound system centered around the Sun. The most prominent objects within this system are the 8 planets. Starting from the Sun and moving outward, we have the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. These planets have solid surfaces predominantly composed of rock and metal. Beyond the terrestrial planets, we encounter the gas giants, Jupiter and Saturn. These enormous planets are primarily composed of hydrogen and helium. Finally, at the outermost reaches, we find the ice giants, Uranus and Neptune. These planets consist of volatile substances such as water, ammonia, and methane. In some contexts, the terrestrial and giant planets are referred to as the inner solar system and outer solar system planets, respectively. The inner planets are closer to the Sun, while the outer planets are more distant. Our solar system came into existence approximately 4.6 billion years ago. It originated from the gravitational collapse of a massive interstellar molecular cloud. As the cloud collapsed, it formed the Sun at its center and a rotating disk of gas and dust known as a protoplanetary disk. Over time, the material in this disk began to clump together, forming planets and various other objects. The fact that the planets all orbit near the same plane can be attributed to their common origin in the protoplanetary disk. In terms of mass, the Sun dominates our solar system, accounting for 99.86% of its total mass. As the Sun radiates energy, it generates a stream of charged particles known as the solar wind. This solar wind creates a bubble-like region called the heliosphere within the interplanetary medium, which itself exists within the broader interstellar medium. The heliopause marks the boundary where the pressure from the solar wind equals the opposing pressure from the interstellar medium. It extends to the edge of the scattered disk, a region populated by various small icy objects. Beyond the heliopause, there is the hypothesized Oort cloud, which is believed to be the source of long-period comets. The Oort cloud is estimated to be roughly 1,000 times farther from the Sun than the heliosphere. It's worth mentioning that the solar system exists within a region of space called the local bubble, which contains the nearest stars. The closest star to our solar system is Proxima Centauri, located approximately 4.2441 light-years away. As we're moving away, we encounter local interstellar cloud. Imagine a vast interstellar cloud spanning approximately 30 light-years across. This cloud, called the local interstellar cloud, is through which our solar system is currently moving. It overlaps with a region known as the solar neighborhood, which encompasses the vicinity around the Sun. However, it's uncertain whether the Sun is embedded within the local interstellar cloud itself or if it resides in the region where the cloud interacts with the neighboring G-cloud. The local interstellar cloud is part of a larger structure known as the very local interstellar medium, which begins beyond the heliosphere and the interplanetary medium. It represents the farthest extent that our space probes have reached. Within this region, our solar system resides in an area called the local bubble. The local bubble is a low-density region within the galactic interstellar medium. The local interstellar cloud has a slightly higher hydrogen density compared to the surrounding space. Its temperature is estimated to be around 7,000 K, similar to the surface temperature of the Sun. However, due to its low density, its specific heat capacity is also low. In fact, it is less dense than the average interstellar medium in the Milky Way but denser than the gas found in the hot, low-density local bubble. To put it in perspective, Earth's atmosphere at the edge of space has a much higher density compared to the local interstellar cloud. The LIC has approximately 0.3 atoms per cc, whereas Earth's atmosphere at that altitude has around 1.2 times 10 to the 13 molecules per cc. The local interstellar cloud is believed to be flowing outward from a stellar association known as the Scorpius-Centaurus association. This association is a region where stars are actively forming. The motion of the cloud is roughly perpendicular to the direction in which our Sun is traveling, assuming a two-dimensional plane. In 2019, researchers discovered interstellar iron 60 Fe in Antarctica, and they associated it with the local interstellar cloud. This finding provides valuable insights into the presence of interstellar material and its interaction with our solar system. Now coming into the bigger picture, the local bubble. The local bubble, also known as the local cavity, is a relative cavity in the interstellar medium. It encompasses various celestial neighbors, including the local interstellar cloud, which contains our solar system, the neighboring G cloud, the Ursa Major moving group, the closest stellar moving group, and the Hyades, the nearest open cluster. This region is estimated to have a size of at least 1,000 light-years. The local bubble is defined by its relatively low neutral hydrogen density, which is approximately 0.05 atoms per cc. This density is about 1/10 of the average for the interstellar medium in the Milky Way, 0.5 atoms per cc, and around 1/6 that of the local interstellar cloud, 0.3 atoms per cc. However, it's important to note that there may be some uncertainty regarding these values. The sparsity of gas within the local bubble is attributed to supernovae that exploded within the past 10 to 20 million years. Initially, it was believed that the pulsar Geminga in the constellation Gemini was the remnant of a single supernova responsible for creating the local bubble. However, it is now thought that multiple supernovae within the Pleiades moving group, specifically subgroup B1, played a role in its formation, resulting in a remnant supershell. Interestingly, our solar system has been traveling through the region currently occupied by the local bubble for the last 5 to 10 million years. Its current location lies within the local interstellar cloud, LIC, which is a minor region of denser material within the bubble. The LIC formed at the intersection of the local bubble and the loop I bubble. The gas within the LIC has a density of approximately 0.3 atoms per cc. The local bubble interacts with other bubbles of less dense interstellar medium, such as the loop I bubble. The loop I bubble, located about 500 light-years from the Sun, was cleared, heated, and maintained by supernovae and stellar winds in the Scorpius-Centaurus association. This association is also home to the star Antares. There are several tunnels that connect the cavities of the local bubble with the loop I bubble, and these tunnels are referred to as the Lupus tunnel. Additionally, there are other adjacent bubbles, including the loop 2 bubble and the loop 3 bubble, which add to the complexity of the interstellar environment. In 2019, researchers discovered interstellar iron in Antarctica, which they associated with the local interstellar cloud. This finding has implications for our understanding of the formation and composition of the local bubble. After enormous distances, we reached Milky Way galaxy. The Milky Way is the galaxy that encompasses our solar system. Its name derives from its appearance from Earth, which is a hazy band of light seen in the night sky formed from countless stars that cannot be individually distinguished by the naked eye. The term, Milky Way, is a translation of the Latin phrase, Via Lactea, meaning, milky circle, and it comes from the Greek phrase, galaktikos kyklos. From our vantage point on Earth, the Milky Way appears as a band because we view its disc-shaped structure from within. In 1610, Galileo Galilei was the first to use his telescope to resolve the band of light into individual stars. However, Observations by Edwin Hubble following the Great Debate in 1920 revealed that the Milky Way is just one of many galaxies. Recent simulations suggest that the galaxy may have a dark matter halo extending up to a diameter of nearly 2 million light-years. It is part of the local group of galaxies, which is itself part of the larger Virgo supercluster, and the Virgo supercluster is a component of the Laniakea supercluster. With an estimated population of 100–400 billion stars, the Milky Way is home to an incredible number of celestial objects. It is also estimated to host at least that number of planets. Our solar system resides at a radius of approximately 27,000 light-years from the galactic center, situated on the inner edge of the Orion Arm. This arm is one of the spiral-shaped concentrations of gas and dust within the galaxy. The central region of the Milky Way, within the innermost 10,000 light-years, forms a bulge with one or more bars radiating from it. At the heart of the bulge lies Sagittarius A*, an intense radio source and supermassive black hole with a mass of approximately 4.1 million times that of our Sun. Stars and gases at various distances from the galactic center orbit at a speed of approximately 220 km per second. It is intriguing to note that the constant rotational speed contradicts the laws of Keplerian dynamics and suggests that a significant portion of the Milky Way's mass, about 90%, is composed of invisible matter known as dark matter. This dark matter neither emits nor absorbs electromagnetic radiation and remains undetectable by telescopes. The Milky Way, as a whole, is in motion, moving at a velocity of around 600 km per second with respect to extragalactic frames of reference. The oldest stars in our galaxy are nearly as old as the universe itself and likely formed shortly after the dark ages of the Big Bang. Next comes the local group. The local group is a galaxy group with a total diameter of approximately 3 megaparsecs, 10 million light-years, and a mass estimated to be around 2 × 10⁻12 solar masses. It exhibits a distinctive dumbbell shape, consisting of 2 collections of galaxies. These 2 collections are separated by a distance of about 800 kiloparsecs, 3 million light-years, and are gradually moving towards one another at a velocity of 123 km per second. The local group, in turn, is part of the larger Virgo supercluster, which itself may belong to the even grander Laniakea supercluster, a vast cosmic structure. The precise number of galaxies within the local group is not entirely known due to some being obscured by the extensive presence of the Milky Way. The 2 largest members of the local group are the Andromeda Galaxy and the Milky Way. Both are awe-inspiring spiral galaxies, each boasting a mass of approximately 10⁻12 solar masses. They each possess their own entourage of satellite galaxies, which orbit around them. As the Milky Way and Andromeda gradually approach each other, it raises questions about their eventual destiny, whether they will collide and merge in a cosmic dance or experience a close encounter with profound gravitational effects. Exploring the local group sparks wonder and curiosity about the intricate connections and vast structures that shape our cosmic neighborhood. It reminds us of the sheer scale and complexity of the universe and our place within it. Let's delve into the fascinating realm of the Virgo supercluster, also known as the local supercluster, LSC or LS. This massive concentration of galaxies encompasses the Virgo cluster, the local group, which includes the Milky Way and Andromeda galaxies, and numerous other galaxy groups and clusters. The Virgo supercluster stretches across an expansive diameter of about 33 megaparsecs, 110 million light-years, harboring a staggering collection of at least 100 galaxy groups and clusters within its vast expanse. It is one of approximately 10 million superclusters observed in the vastness of our universe. It serves as a gravitational anchor for a multitude of galaxies and plays a significant role in shaping the large-scale structure of the universe. Finally, the observable universe. The observable universe refers to a ball-shaped region within the vast expanse of the universe that encompasses all matter and objects that can be observed from Earth or through space-based telescopes and exploratory probes. The key criterion for inclusion in the observable universe is that the electromagnetic radiation emitted by these objects has had sufficient time to reach the solar system and Earth since the beginning of the cosmological expansion. It is estimated that there may be around 2 trillion galaxies within the observable universe, as suggested by some studies. However, more recent data from the New Horizons mission has revised this estimate to several hundred billion galaxies. These galaxies contain a vast array of celestial objects, such as stars, planets, nebulae, and other structures. In other words, the observable universe can be visualized as a spherical region centered on the observer. However, it's important to note that every location in the universe has its own observable universe. Each location's observable universe may or may not overlap with the one centered on Earth. Therefore, different observers in different parts of the universe would have their own distinct observable universes. The universe vs. the observable universe. The size of the entire universe is still unknown, and it is possible that it extends infinitely. However, there are parts of the universe that lie outside the observable universe. Therefore, we are unable to observe them directly. However, there are limitations imposed by Hubble's law and the expansion of the universe. Regions that are sufficiently distant from Earth are expanding away from us faster than the speed of light, making it impossible for their light to reach us. Furthermore, the expansion rate of the universe appears to be accelerating due to dark energy. Under the assumption that dark energy remains constant and the universe continues to expand at an accelerating rate, there is a future visibility limit. This limit represents the point beyond which objects will never enter the observable universe, even in the infinite future, because their light will never reach Earth. The future visibility limit is calculated to be at a comoving distance of 19 billion parsecs, 62 billion light-years, assuming the universe will continue expanding forever. This implies that the number of galaxies we can theoretically observe in the infinite future is only slightly larger than the number currently observable, with a factor of 2.36. In practice, as the universe expands, an increasing number of galaxies will become extremely red-shifted. This means that their light will be stretched to longer wavelengths, eventually making them invisible to us. These galaxies will seem to disappear from view due to ongoing expansion. Additionally, due to the expansion of the universe, there may come a time when even signals sent from galaxies within the observable universe at earlier ages will never reach Earth in the infinite future. This is because the universe's expansion can prevent the signal from reaching us, even though the galaxy remains at the same comoving distance. This concept gives rise to a type of cosmic event horizon, whose distance from Earth changes over time. Currently, the distance to this horizon is approximately 16 billion light-years, meaning that an event happening within 16 billion light-years of us can eventually have its signal reach Earth, while events beyond that distance will never be observable to us. These limitations and the complex nature of cosmic expansion add an element of excitement and curiosity to our understanding of the universe. Exploring the boundaries of what we can observe and the mysteries that lie beyond them encourages engagement with the vastness and intricacies of the cosmos. Thank you. Please like and subscribe.